Okay, so we're going to use calculus to show that the volume of a cone is given by 1/3 pi r squared h. R is the radius of the circle on the base, and h is the height of the cone. And so the way we're going to do this is we're going to be essentially adding up a bunch of cylinders with infinitesimally small heights as we go up the height of the cone. And calculus is good for this because the radii of those circles are changing over time, right? As we're going up. So how are we going to do this? Let's draw one of those circles, and that has some radius. I'm going to call it I'll call it y. Okay, and that y value initially is r, but it's going to go up to 0 at the top of the cone. Okay, but this, remember, is a cylinder, so we're doing volume, and so we're going to give that a height dx, and we're going to be calling this our x coordinate here. So at the bottom here, we're at x equals 0, is what I'm going to define at the base. At the top, we're at x equals h. So then the volume is just going to be the integral adding up, right, from 0 to h of, what's the area of the cylinder? Well, that's pi y squared dx, right? Because it's a volume, area of the circle times the height, that's the volume of the cylinder. Infinitesimally small, dx height cylinder. Okay, so now we just have to get y and x, y basically in terms of x. And so what do we know about x? Well, we know that at x equals 0, y equals r, right? Because at x equals 0, the radius of the circle is, we're at the base, so it's r. At x equals h, y equals 0. And so now we have 2 points and we have a line, and you notice that, you know, the edge of the cone is a line. The radii of these circles, these cylinders, is linearly decreasing as we move up the cone. And so we essentially have a y equals mx plus b type relationship, right? A linear relationship. And so our slope here, m, we can calculate. That's going to be rise over run, right? Delta y over delta x. And that's going to be r minus 0 over 0 minus h. That's negative r over h. Okay, so let's continue plugging that in. Y equals, now m is negative r h times x plus b. Let's plug in one of these points. So at x equals 0, y equals r. So that whole term is times 0, so that goes away, plus b. So that tells us that b equals r, or r equals b, right? Good. So now we have both our m, our slope, and our intercept, our b, and we can put those in. So our intercept is r, and our slope we figured out before. At this point, we just have to plug this in for y. And so we're going to get 0 to h pi y squared. Well, y was negative r over hx plus r, square of that dx. Okay, and so now we can expand this out a little bit. We have a constant pi in the front, so I'm going to put that in front of the integral constants you can put out in the front. And we're going to have negative r over h x times itself squared. That's going to be our first term when we expand this. So we're going to have r squared over h squared, and that's going to be x squared, right? And then we're going to have minus 2. We're going to have 2 terms, r over h r squared, though, because we're timesing r over h times r. So r squared over h times x. And then our last term is just going to be plus r squared. And all that, again, is times by dx. And so let's just copy that over to the next slide. Okay, so this is what we had. for our first integral, or for our integral at this point. And now we just gotta expand this out. We have 3 terms here, so we can expand out into 3 different integrals, bringing out the constants. So r and h are both constants of the cone, right? And so we're just gonna have 0 to x of x squared dx, and then we're gonna have a minus 2, and that's an r squared over h, and from 0 to h of x dx. Then we have a plus, and that was r squared 0 to h of dx. And so now we can evaluate all these integrals. Integral of x squared is 1/3 x cubed. Integral of x is 1/2 x squared. And the integral of dx is just x. And so at this point, we're going to have pi r squared times h squared times 1/3 h plugging in for x cubed minus 1/3 0 times 0 cubed minus 2r squared h, and that's going to be 1/2 our h plugs in for x there, so 1/2 x squared minus 1/2 0 squared, and then plus r squared times h minus 0. And so all these 0 terms are going to go away. We're going to end up with just this first term. So let's cancel that. Let's just cross out these 0 terms. Okay, so we don't have to look at these. Now we have pi r squared over h squared times 1/3 h cubed. Well, we have an h cubed in the numerator and an h squared in the denominator, so that's going to go away. We're going to end up with pi r squared h 1/3. Okay, and then we have minus, let's see, 2 in the numerator, 2 in the denominator, and we have h there, h squared and an h in the numerator, so that's going to be minus r squared h. And here we just have plus r squared h, and so minus r squared h plus positive r squared h goes away, so we'll end up with our final answer of 1/3 pi r squared h equals our volume, which is what we know from general geometry, but it's pretty neat to see that proven using calculus.